All right, so this is a recording of the lecture we've viewed today on Zoom. Support vector machines, outline of the lecture, setup, model, and then we'll talk about support vectors, which is really the most important part of the lecture. So the idea is we assume linearly separable data for this lecture, and then we'll look at how to deal with non-linearly separable data in the next one. So that's an example of linearly separable data. It's obvious that a line can separate these two sets of points, the red and the blue. There's an infinite number of separating lines. So here are three examples of these lines, and one is better than the other, right? They're all the same. With respect to the n-sample error, all have an n-sample error of 0 because they correctly classify all four points. All the same as far as generalization is concerned because they're line, so the same number of parameters, and it's the same training set, so 4 points. But line 3 is least overfit to the data, obviously. Right? It would not classify points, new points wrong as much as line 1, for instance. So we have an infinite number of separating lines. Think of a margin of error. If crossed, the line will start making errors. The margin is the distance to the closest point. So this is what's shown using the yellow bars here. So obviously L3 had the largest margin, yeah? So if you see L1, the one on top here, this is very likely to misclassify red points, yeah? Because any red point that comes here, for instance, would be misclassified as blue. So larger margins imply less overfitting. New points are more likely to be classified correctly. So just to talk about large margins in respect to generalization. How many dichotomies using a line on 3 points? We have 8 possible dichotomies, right? Everything positive, everything negative, 2 positive, 1 negative, and so on. So growth function is 2 to the power 3, which is equal to 8, so very poor generalization on 3 points, yeah, because it has the upper bound, 2 to the power of n. Again, large margins imply fewer dichotomies. So if we look at the margin for the different dichotomies, for different lines representing the different dichotomies, the 8 different dichotomies, we have, for the first one, the margin of error is infinity. Why infinity? Because I want the line to be as far away from the points, data points, as much as possible, right? So to classify all the points as positive, I can put the line here, right? So as far away from these points as possible. It has a margin of infinity. Same thing for the negative, all negative case. For 2 points positive and 1 negative, the line that achieves the highest margin or the largest margin is the line in the middle here, yeah? And this is the margin, the distance to the closest point, and it happens to be 0.866 in this example. It's 0.5 in this example, and so on, yeah? Now, if I restrict the set of hypotheses to those whose margin greater than or equal to 0.866, I'm reducing the degrees of freedom. So I'm not allowing the model to just choose any line. It's choosing only lines that satisfy this constraint. Yeah, so the four rightmost dichotomies are no longer possible because they have a margin of error less than or equal to 0.866. Okay, so how does this help? This idea of margin of error and maximizing it when it comes to classification. So the setting is as usual. I have d-dimensional space and in now linearly separable points x1, y1, x2, y2 until xn, yn. The hypothesis is sine of summation from I equal 1 to d wi xi plus b. So I explicitly model the threshold here, b. Yeah? And this is in vector form is sine w transpose x plus b. Great. Now w transpose x plus b equal to 0 is a hyperplane. In 2 dimensions, this would be an equation of a line. Okay. And I classify the points based on, right, the sign of w transpose x plus b. So if this is positive, I say positive or plus 1. If this is negative, I say negative. Yeah, so I substitute with the value of x, multiply by the weight and add the threshold b, and that gives me, and take the sign, and that gives me the prediction. Our goal is, as usual, to find w and b that make the hyperplane perfectly separates the data, so I make no errors at all, and maximize the margin. So because there is an infinite number of hyperplanes that can separate the data, I want the ones that maximize the margin, i.e. the distance to the closest point, to be, in the middle between the positive class and the negative class. So perfectly separating the data, we're gonna write this mathematically. So I have w transpose x plus b is equal to 0. Again, this is the equation for the hyperplane, and it perfectly separates the points if for every point xi in my data set, w transpose xi plus b is greater than 0 if yi is greater than 0. Yeah, so they agree on the sign. Remember that my prediction is sign of w transpose xi plus b. And I want this to be positive when the label is positive and negative, so less than 0 when yi is less than 0. I'm going to write this into one line. So w transpose x plus b equal to 0. This hyperplane perfectly separates the point if for every point in the data set xi, yi times w transpose xi plus b is greater than 0. Yeah, this means that they agree on the sign. Now maximizing the margins. Now I have already modeled how do I show that the hyperplane linearly separates the data. Now let's see how do I maximize the margin. The margin again is the distance between the hyperplane and the closest point in the data set. So the equation of the hyperplane is w transpose x plus b equal to 0. Let xn be the closest point to the hyperplane. Xn is just one of the training examples. So here's xn, here's the hyperplane. I want to measure the distance between xn and the hyperplane. First remark we're going to make is that the vector w is perpendicular to the hyperplane in the x space. How is that the case? Take any 2 points x dash and x double dash on the hyperplane. Since they are on the hyperplane, they satisfy the equation of the hyperplane. So w transpose x dash plus b is equal to 0, and w transpose x double dash plus b is equal to 0. Okay, we can subtract these two equations, and we get w transpose x dash minus x double dash is equal to 0. What does this mean? This is a dot product between a vector w transpose and a vector x dash minus x double dash, and the dot product is equal to 0. That tells me that w is perpendicular to the vector x dash minus x double dash. Okay, so we established that w is perpendicular to the hyperplane. Okay, now let's measure the distance between between xn and the hyperplane. We're going to take any point on the hyperplane. Okay, so let's call this point x. Then the distance between xn and the hyperplane is given by the following formula, right? We've shown this in the Zoom lecture using a line. So the division is to use, right, the cosine, the angle between xn minus x and the vector w. and do some simplification, and that tells me that the distance is 1 over norm W absolute W transpose dot product xn minus x. Okay. Again, remember that W is perpendicular to the hyperplane in the x space. Okay, we can simplify this formula. So the distance is 1 over norm W, W transpose xn minus W transpose x. Add B and subtract B. And now I can do some simplification. I know that W transpose x plus B is equal to 0 because x lies on the hyperplane. I get that the distance is 1 over norm W, W transpose xn plus B. So it depends on xn and the vector W and the value of the scalar B. Okay, so that's the distance. Now the SVM optimization problem is stated as follows. Our goal is to maximize the margin. So I want the distance to the closest point to be as maximum as possible. Right, so maximize 1 over norm W absolute W transpose xn plus B, because that's the distance between the point xn, the closest point, and the hyperplane. And I want the data to be linearly separable. So not any hyperplane, because I mean the one that maximizes the distance to xn would be the one that is at distance infinity. Yeah. So I want to make sure that the hyperplane linearly separates the data. So yi W transpose xi plus B is greater than or equal to 0, is greater than 0, sorry, for I equal 1 till n. So for every data point. This is a very ugly optimization problem, so we're going to simplify it a little bit. We're going to assume that absolute W transpose xn plus B is equal to 1. That's the same hyperplane what was B and W scaled. So you scale W and B, you divide whatever this value was, absolute W transpose xn plus B was, right? I divide I normalize to get it to be 1. Yeah, that tells me that it's the same W, the same hyperplane, but with W and B scaled by the same factor. Okay, so we're going to rewrite the objective function and the constraints so that we get the following. I wanted to maximize 1 over norm W times 1 now, because W transpose xn plus B is equal to 1. So instead of maximizing 1 over norm W, I will minimize norm W. And norm W is nothing but, right, the square root of W transpose W. So I can minimize W transpose W instead. And multiplying this by half doesn't change the objective function. Yeah, we'll see why the half, because we're going to do differentiation and the half will eliminate the square. And subject to, right, the constraint was before yi W transpose T W transpose xi plus B is greater than 0 for every data point. Now it's yi W transpose xi plus B is greater than or equal to 1. Why is this greater than or equal to 1 and not 0 anymore? Because of the following observations. We have W transpose xi plus B, absolute this value is greater than or equal W transpose xn plus B. Why? Because this is xn at the closest point to the hyperplane, and so all the other points, right, would have distance greater than or equal to absolute W transpose xn plus B, because that's the closest point to the hyperplane. That's the first observation. Second observation is that absolute W transpose xi plus B is equal to yi W transpose xi plus B, because the data is linearly separable. So this is, right, is greater than 0, and so it's the same as the absolute of W transpose xi plus B. Okay, from these two equations or two observations, we get that yi W transpose xi plus B is greater than or equal to 1. All right, let's talk about the model. So the model is the one that solves this optimization problem. Minimize half W transpose W subject to Yi W transpose Xi plus B is greater than or equal to 1 for every data point in the training set. It's a constrained optimization problem, and it can be solved using Lagrange formulation. That's a general method for solving constrained optimization. So how do I convert this into the Lagrange form? I take my objective function and subtract every constraint that I have in the zero form. Okay, so I have minimize half W transpose W minus, I have n constraints, right? So I subtract these n constraints in the zero form. Every constraint is Yi W transpose Xi plus B minus 1. That's in the zero form. Multiply this by a Lagrange multiplier lambda I. Okay, and since I have n of these, then it's summation from I equal 1 to n lambda I Yi W transpose Xi plus B minus 1. Great. Now all I have to do is minimize L, the loss function, with respect to WB and maximize it with respect to lambda I, where for I equal 1 to n, I have lambda I is greater than or equal to 0, so that comes from the Lagrange formulation, and lambda I Yi W transpose Xi plus B minus 1 is equal to 0. Okay, so basically either lambda I is equal to 0 or Yi W transpose Xi plus B minus 1 is equal to 0. Okay, for every point I equal from 1 till n. Okay, so how do I minimize this loss function with respect to W? I differentiate with respect to W and equate to 0. So I take the partial derivative of the loss function with respect to W and equate to 0. Okay, so let's do that. I have half W transpose W. That's as if I'm saying half W squared. So it becomes half times 2W. The 2 cancels the half and I get W. Okay. Now the second component, right? I have summation. So minus sigma from I equal 1 to n. I have lambda I Yi Xi times W transpose. That becomes, if I'm differentiating with respect to W, that becomes lambda I Yi Xi. And then the second component is B. It doesn't depend on W, so it goes away, and the minus 1 goes away. It's constant with respect to W. Okay, so I get that W is equal to summation from I equal 1 to n lambda I Yi Xi. Okay, so that's the first equation, right? The only unknown is lambda. So if I get the lambdas, right, for every data point, I can get the value of W, the vector W, okay, which are the same dimensions as the vector Xi. So there's one W for each feature. Minimizing L with respect to B, the same thing. I'll differentiate and equate to 0. First component, half W transpose W, doesn't depend on B, so it goes away. And then I have minus sigma from I equal 1 to n lambda I Yi W transpose Xi also doesn't depend on B, so it goes away. I get minus sigma I equal 1 to n lambda I Yi is equal to 0. Why? Because this is multiplied by B. Yes, when I differentiate, the B goes away, and I get minus summation from I equal 1 to n lambda I Yi is equal to 0. So from this I get that summation from I equal 1 to n lambda I Yi is equal to 0. I substitute back in the loss function with the value of W and using this equation for lambda I, summation of lambda I Yi. And then the loss function will be in terms of lambda alone, and then I can solve for lambda and get the values of W and B. Okay, so let's substitute back. I have half W transpose W, that's double summation then of lambda I, lambda J, Yi, Yj, Xi transpose Xj. Okay, so I have half of this minus summation from I equal 1 to n lambda I Yi And then W transpose is summation from I equal 1 to n, or from summation to be exact from j equal 1 to n, lambda j, yj, xj. Okay? So I have double summation, lambda I, lambda j, yi, yj, xi transpose xj. That's in the with a minus, and I have half of this positive, so I get minus half double summation lambda I, lambda j, yi, yj, xi transpose xj. Okay, and then substituting that summation from I equal 1 to n lambda I, yi is equal to 0, I get that sigma from I equal 1 to n lambda I, yi times b goes away, that's 0, and I only left with minus summation from I equal 1 to n lambda I times negative 1, and that becomes summation from I equal 1 to n lambda I. Okay, so now this loss function depends only on the lambdas. If I get the lambdas right, that's the only thing that is unknown. If I get them, I can solve back for W and B together. Okay, so that's a quadratic program. Why quadratic program? Because I have lambda I times lambda j. Yeah, so they're multiplied by each other, so it needs a quadratic program. Similar to a linear integer programming. Yeah, so an optimization technique that is used to solve optimization problem. So I want to maximize the loss, right? Now written in terms of lambda with respect to the lambda i's for I equal 1 to n, and given that summation from I equal 1 to n, lambda I, yi is equal to 0. Okay, so I'm going to write this in vector form. I'm going to minimize instead of maximizing, so I multiply by negative 1, half lambda transpose times the matrix Q times lambda plus minus 1 transpose lambda, right? Lambda is now a vector which has n components, lambda 1 till lambda n. Okay, and what is the Q matrix? It's this matrix, right? Y1, Y1, X1 transpose X1, Y1, Y2, X1 transpose X2, and so on. So it depends entirely on the training data. I can construct this matrix from the training data, similar to when we constructed the pseudo-inverse in linear regression. Okay? Now, I want to minimize half lambda transpose Q lambda plus minus 1 transpose lambda. That's exactly the same as the above objective function here. Yeah? And subject to, I have summation from I equal 1 to n lambda I, yi is equal to 0. That's in vector form. Y transpose lambda is equal to 0. Yeah? Basically, y is a vector transpose, and lambda is a vector. If I multiply them, do I dot product, that gives me summation from I equal 1 to n lambda I, yi. Okay? And I have lambda is greater than or equal to 0 and less than or equal to infinity, because I know that every lambda I is greater than 0. Okay? Now, I give this to any library that solves quadratic programs, and it will give me back values of lambdas, right? So give me back n lambdas, lambda 1, lambda 2, until lambda n. I can now substitute in the equation W is equal to summation from I equal 1 to n lambda I, yi, xi to get W. This equation we got by differentiating the loss function and equating to 0. The only unknown was lambdas. Now I have them. Yi is the label, xi is the feature vector. So if I sum these guys, I get the W. Now how do I get the B? Recall that I have lambda I, yi, W transpose xi plus B minus 1 is equal to 0. That was when we wrote the Lagrange formulation of the objective function. Okay, so I have two cases. When lambda I is equal to 0, and when lambda I is not equal to 0. When lambda I is equal to 0, I get that yi w transpose xi plus b is greater than 1. Okay, so not equal to 0. And when lambda I is not equal to 0, then the second component has to be equal to 0, right? Because so that the multiplication is equal to 0. So I get yi w transpose xi plus b is equal to 1. Okay, what does this mean? For the first case, when lambda I is equal to 0, I have xi as an interior point, yeah, because yi w transpose xi plus b, so absolute of w transpose xi plus b is greater than 1. That tells me this is not the closest point to the hyperplane, because we assume the closest point to the hyperplane have this value equal to 1. And when yi w transpose xi plus b is equal to 1, I get xi as a support vector. So it lies on the margin. It's one of the closest points to the hyperplane. Now to get b, I use the equation that yi w transpose xi plus b is equal to 1. So take any support vector xn that satisfies the inequality yn w transpose xn plus b is equal to 1. Divide by yn, that's the same as 1 over yn, so w transpose xn plus b is equal to 1 over yn. 1 over yn is equal to yn, yeah, because yn is plus 1 or minus 1. So you get b is equal to yn minus w transpose xn. I know the w already, I computed it using this equation. I have yn, it's a label, and xn is a feature vector. I get the b, yeah? It's obviously a scalar. Yn is a scalar, and w transpose times xn gives me, dot product gives me a scalar. Okay. So I got the w and the b. I've solved my problem. I got the model. Let's talk about support vectors, right? Very important. So what are support vectors? These are the closest points xi to the hyperplane in the training set. These are the points that achieve the margin. Basically, that yi w transpose xi plus b is equal to 1. So if I have this training set, the points on the margin are going to be the support vectors, right? I'm gonna circle them. And these are the support vectors. If xi is support vector, then the lambda I corresponding to it would not be equal to 0. Otherwise, it is 0. Right, and in practice we would have fewer support vectors than very few support vectors in the training set. Yeah. Now w is really summation over xi is a support vector, so over the support vectors lambda I yi xi. Why? Because for the rest, lambda I is equal to 0. So instead of summation over all the data points, lambda I, yi, xi, I'm just summing over the support vectors, because for the others, lambda I is equal to 0. Okay. So what is the effective number of parameters? It's really the lambda i's corresponding to support vectors, because the rest are 0. So the degrees of freedom here is reduced to only write the number of support vectors. There is a theorem on the generalization of support vector machines that the expected of the E out is less than or equal to expected number of support vectors divided by n minus 1. So if you have a data set and that has 1000 points and let's say hundreds of features, right? The effective number of parameters is not going to be dependent on the number of features, but on the number of support vectors, which are usually few. And this is why support vector machines are very powerful, right? So they generalize very well because, right, the number of effective parameters is small. Okay. Nonlinear transforms, we're going to talk about them in the next lecture. Thank you.